Okay, thank you very much for the kind introduction, and thank you for giving me this great symposium. Thank you for inviting me to this great symposium. And I hope that today's talk will initiate a collaboration between NTU and KAIST. Okay, so today I'm gonna talk about a new class of 2D material. Basically, I'm working on 2D material growth. And today I will introduce the recent advances in 2D materials in terms of new 2D semiconductor materials. So let me first begin with the brief introduction about the 2D layered semiconductor. Okay, so the layered semiconductor have been studied a lot due to their unique crystal structure. And unlike the conventional semiconductor such as silicon, the layered semiconductor literally have a lateral crystal structure where the out of plane direction has the van der Waals bond and the in plane direction has covalent bond. Because of such a structural anisotropy, we can design the materials that cannot exist in the nature. For example, the extremely thin materials, so-called monolayer material, a lateral heterostructure and vertical heterostructure can be formed using based on this material system. And for the semiconductor application point of view, this layered structure has a great advantage. For example, compared to silicon, or a 2D layered semiconductor doesn't have the dangling bond, and which doesn't have a dangling bond free surface, which can minimize the surface scattering. Therefore, the mobility decay, depending on the thickness and the leakage current in the thin channel can be suppressed, which is required for the next generation semiconductors, such as the gate-all-around transistor or ultra-thin band transistor. And the second advantage is that the layered materials are intrinsically crystallized well, even on the amorphous surface. Imagine, and I have never seen the 1 nanometer thick semiconductor material that can be uniformly grown over wafer scale on the amorphous surface without any, without the crystalline wafer. So which is this material is basically crystallized well and with the ultra thin thickness, which is very amazing. And based on using this property, we can stack another channel material on the CMOS circuitry so that we can stack up, and then we can generate the 3D integrated circuitry. And last advantage I prepared today is the epitaxial growth. Again, thanks to the no dangling bond surface allowed us to form a large lattice mismatch combination of epitaxy through van der Waals interaction, which is also unique material growth phenomena, and it can be applicable for the optoelectronic devices, I imagine. Okay, for now, the most popular materials in the such 2D layered semiconductor is transition metal dichalcogenide, which is a compound of transition metal and chalcogens, so-called TMDCs. And let me introduce the history and current status of 2D TMDC growth. In the beginning, TMDC growth was basically vapor transport of powder or the powder-based CVD. And of course, thanks to the pioneers, we understood the basic property of 2D TMDCs, but it was a lack of compatibility for thin film process, and the controllability was always the issue. Therefore, of course, we need a gas phase growth method for the application, for example, such as the MOCVD technique. However, there was nucleation control issues in MOCVD growth, since the growth environment is too reactive, so that the nucleation control was really difficult, which means that the grain size is extremely small, and then the semiconductor for the semiconductor channel materials, grain size should be big to minimize the scattering between the grain boundary. And accidentally, we found that the alkali metal salt can suppress the nucleation density dramatically and then improve the electrical and optical properties. So now the use of alkali metal salt became a quite general method to control nucleation in 2D material growth field. With the advanced nucleation control and 2D TMDs can be formed also a unique lateral heterostructure like these images. You know, the direction of the synfilm deposition is naturally vertical. You know, deposit A and deposit B, which is pretty general. However, with the 2D layered structure, we can form the lateral direction heterostructure. And now we are looking at the MOS2 and polyselenide monolayer heterostructure, where the width can be controlled within the 10 nanometer, which is very amazing. And using the monolayer 2D TMDs as a building block, we can stack one layer by one layer, and we can generate the beautiful 2D super lattice with ultra clean interface like this. Okay, so the 2D semiconductor studied a lot, and then the material system. But the problem is that the material system was quite limited to the MOS2 and MOS2, which you have heard a lot of time for a while. So then what would be the next in terms of extension of the material class? And regarding the binary transition metal system, my colleague Zheng Liu at NTU reported the brilliant work that reported growth of various 2D TMDs and corresponding properties. So basically, they generate a library. I like this title, a library of 2D TMDs. Then, okay, so then what can we, the study of 2D TMDs was done actually now. So, and thanks to the high throughput simulation technique, now we have material classification data for the 100,000 of crystal system. And now we know that there are thousands of layered materials, and among them, only few of them in the gray color area, only few materials are discovered, and the rest of the materials are metastable. So thanks to such a simulation, now we know the layered material system that can be possibly formed. Of course, it's theoretically, but now we know we have some guidelines to study the new material and for the extension of the material system. Of course, it's really hard to grow new material, but we want to discover and we want to push to discover new layered materials from this for the 2D materials. Okay, and then for this sense, I believe the ternary oxy-chalcogenides and alkali metal intercalate 2D material could be one of the candidates. So yeah, today's talk content is like this. Okay, the first one. So previously, until now, I have introduced the binary system, transition metal and chalcogen. What if we add one more element, that is the oxygen? And this ternary material system, among this ternary material system, recently bismuth oxy-selenium, this ternary combination is quite emerging. The reason was that this bismuth oxy-selenide also have the layered structure, and let me show you this diagram. And compared to the TMDC material, for example, molly sulfide and tungsten selenide, the electrical mobility is much way higher than the 2D TMDCs, and the optical property, for example, the polar response, and especially IR region. So compared to the 2D TMDC, this ternary system has have an advantage in terms of electrical and optical properties. And recently, we have developed a large-scale MOCVD growth of such this ternary system, bismuth oxy-selenide growth at very low temperature, even just 300 degrees Celsius. And then what you are looking at is that the monolayer bismuth oxy-selenide grows on strontium titanium oxide substrate, STO substrate. And then the controllability is pretty nice, and so that the monolayer bismuth oxyselenide grows on the step of the monolayer step of STU, and then we can generate the monolayer bismuth oxyselenide. And then we can control from the monolayer and bilayer. And if we spend more time, we can generate the thick epitaxial film like this. And then, of course, this materials can be applied to the large scale closed system. And here is the representative, the crystal structure data, and where the between the bismuth oxyselenide and STU, it's nicely formed epitaxial film. So that here is the theta to theta scan, and then actually this one is the in-plane lattice method. To confirm the in-plane lattice structure, we try the RSM measurement, and it formed the epitaxial film. And then as I introduced this bismuth oxyselenide, expect to have the good electrical mobility, and then we generate the FET devices, and then it shows the very high mobility. And if for generally the thin film semiconductor, it's really difficult to get the over 100 centimeter scale the mobility, and it shows a very nice mobility. And in terms of the photo detection, using this material, this material have a NIR band gap, and the band gap is much smaller than the silicon case, and so that we can generate the NIR response photo detector like this. And here is the one take-home message. And normally I do not use this slide for the seminar, but now I'm wanting to have get some collaborator between NTU and KAIST, so that one of the interesting points is that bismuth oxyselenide, the lattice constant is quite exactly matched with the silicon, and so that when you look at this table, when we can mix with sulfur and tellurium, so that we can basically control the lattice constant. Plus, we can also control band gap, and this TMOC material system potentially can be epitaxially grow on the silicon. And not only the silicon, actually we already demonstrated this material can be grow on the STO substrate, so that the perovskite oxide also one of the candidates to combine with this material system. Yeah. Okay, second topic I would like to introduce is the 2D oxide. Since Chris, I would like to remind you that I'm looking for some new material system and extension, and beyond the previous method. So in terms of manganese oxide material system, there are many kinds of the phases and the polymorphs, and there is the layered crystal structure that's known. But the problem is that the layered structure mangan oxide, that is the delta mangan dioxide, this material, this phase is unstable and metastable, so that people couldn't get the 2D manganese oxide because this is unstable. However, what we have found is that with the alkali metal intercalation, the delta mangan oxide can be stable. So we can generate the unstable material by using the alkali metal intercalation. And here is the representative images. So while we grow manganese oxide, if we introduce alkali metal precursor together, then we can generate the layered structure manganese oxide like this. And then this is the representative optical images. And as you can see, there is the very nice flake of manganese oxide. And here is the corresponding XRD data and then Raman data. And the thickness, well, it's about 10 nanometer scale, but we can also generate the thinner than 10 nanometer as well. And here is the TM lateral, the cross-sectional TM image of the manganese oxide. oxide. And then if you look at carefully, and here is the manganese oxide layer, and in between there is a potassium intercalated atom in between like this. And then EDS mapping also tells us the potassium is there like this. And actually, the manganese, we have reported manganese oxide this year, but currently we also grow the cobalt oxide as well. So just by change the metal precursor to cobalt, and then we can grow the cobalt, potassium cobalt oxide. And now we also switch the alkali metal from the potassium to sodium. And now we can also grow sodium cobalt oxide. Of course, sodium intercalation is much difficult than the potassium case, because the sodium cobalt oxide, this material is likely to de-intercalated after growth. But actually, this is also a very interesting situation, depending on the metal oxygen combination plus the alkali metal combination. Depending on such a combination, we can design the new layered material that we haven't seen before. Okay, and another thing, in terms of the device demonstration, can you see this video? Using the potassium mangan oxide, and then if when we put the electrode on top of them, and when we apply the electrical field, then the potassium ion can be diffuse the opposite direction. When we apply the positive bias, then potassium ion is moved from here, this electrode, to the next electrode direction. So basically, we can tune the alkali metal the ion concentration inside of this flake, and then and which is reversible. So it is, and depending on the alkali metal ion concentration, this material, the optical characteristic and electrical characteristic is changed, as you can clearly see in this video. So it is pretty also interesting. And using such a situation, we can design synaptic device based on ion transport, so that here is the synaptic device, the analog resistive change. So depending on pulse we apply, there is the synaptic behavior. And interestingly, in case of cobalt oxide, it shows the much larger the ratio of the high current and low current region. So yeah, so as I suggested, depending on the metal and alkali metal combination, we can optimize the best performance for the targeting devices. And we also demonstrate the spike timing dependent plasticity, and which is also ongoing research for now. Okay. And I also have another suggestion for the 2D the metal oxide case. The between the synapse, basically the communication element is alkali metal ion. So many people say the synaptic device is mimicking the neuron synapse, but basically the synaptic devices mimicking their function, not their mechanism exactly. So what we are looking for is that, what if we can just deliver or communication based on the alkali metal ions like this, so that we can design the pre-synapse and post-synapse, and then we can communicate each device based on using the alkali metal ions, and then later maybe we can also put some real synapse on top of these devices. It can also generate the synapse, the neuron to the electrical device communication as well. We can realize such some new concept of devices as well. Okay, so here is the end of my talk, and yeah, thank you for your attention.
Thank you very much for a fantastic presentation. I was really impressed. So I will open up the Q&A session. So if you have any questions, please bring up. During the preparation of the questions, actually, I have a lot of questions about your presentation. And my first question is, so probably the just two-dimensional without oxide, the bismuth uh, selenide is also probably another two-dimensional material. Then how can you actually selectively fabricate bismuth oxy-selenide instead of bismuth selenide?
Oh, that's a great question. So yeah, bismuth selenide also layered material system. So without oxygen, we can get bismuth selenide, but bismuth selenide is yeah, also a popular study because of their topological insulator properties. No, it's topological insulator. There are many interesting phenomena, but basically it is a semi-metallic property. So if so, it's pretty tricky. Find the optimum growth window between the bismuth oxygen and selenium. Yes, but yeah, actually, so thanks to such phenomena, not only bismuth oxyselenide 2-to-1 phase, we can actually keep generating some new phase. For example, we can also generating 7.56 phase. This is also pretty interesting combination between among these three elements, and we are also keep looking for another phases among such ternary system.
I see. Does the fabricated bismuth oxyselenide have oxygen vacancy, and does it affect the electrical properties as well?
Oh, okay, okay. So you are saying that. So actually, maybe I didn't explain details. So in case of this case, the potassium ion is just intercalation, so and they are quite free. But in case of the bismuth oxyselenide, they have the strong bond. Basically the one layer from the bismuth oxide, and there is a selenium layer, and basically this unit cell they have the strong bond. So yeah, of course the oxygen vacancy is very critical. So plus all the oxide material, the oxygen vacancy can generate the kind of electrical doping, so that if there is a many oxygen vacancy, it became quite metallic material. So as you say, yeah, oxygen vacancy, controlling the oxygen vacancy is also important. So, but for now, our optimal growth condition, we can generate quite low level of oxygen vacancy, and then we can get the high performance transistor.
Professor Kang, just out of curiosity, actually, I'm not tracking that much about this side now, but so actually we made some tungsten oxide and moly dioxide out of disulfide by oxidation. So actually you showed some CVD growth of oxides. So is those oxides stably can exist as one layer oxide?
You mean the manganese oxide?
Not only manganese oxide or some general other oxides?
Okay, that's also a great question. So you told me as an example the moly oxide and tungsten oxide. Yeah, yes, they can form the layered structure, but the problem is the interaction between layers. Their interaction is quite strong. But yeah, where I cannot say, but yeah, but so that was the issue, that separation from the layer to layer. That was the issue for the moly trioxide and tungsten oxide because of the interaction. Yes, and in case of the manganese oxide, it's regarding the chemical stability, the layered structure plus the monolayer manganese oxide. It's difficult to form chemically stable, the monolayer. Yeah, that's the.
Yeah, so actually that's my general question. I mean, the oxide 2D material. So mangan oxide case looks like there's definitely some stable 2D basis. But the tungsten oxide is it known very stable 2D phases. So only the difficulty is the exfoliation, not the material itself.
That's what I know. So the moly trioxide, it is the layered structure. molly trioxide. Maybe tungsten case I don't know, but a molly trioxide is obviously layered structure. Yeah.
I see. So there are certain phases of 2D oxides, but the exfoliation is more difficult.
Yeah, exactly. Yeah.
I see. Also, one quick question. So, for example, like the old layered material society, MB was a very powerful and useful tool. But I think I did not see much of the scientists, especially the gross 2D material scientists, actually use MB. Is there any special reason?
Yeah. So I think I'm not an expert in the MB, but what I know is that the controlling the sulfur vapor is extremely difficult. So that there are some report about molybdenum selenide. So selenide is doable, but sulfide is less difficult. And another issue is that the layer control is also it's difficult. So basically, the mechanism of the forming the monolayer is that the lateral direction is quite chemically reactive, and then top surface is quite the top base plane is chemically unreactive. So the chemical reaction between the existing flake and then incoming the element from this situation, the monolayer material can be grown. But in the MB case, it's introducing the element, so it's more difficult to control the layer, the number of layer than
Actually, let's go back to my question again. So if there's a stable oxide layer or something like that, then maybe those MB should be possible. But yeah, I'm not the expert, but just curious.
Yeah, there are many reports about the growing the the monolayer or epitaxial growth using MB, but if we targeting the growth on the amorphous surface, it's obviously the MB growth is more difficult. But in the MB society, they also studying the TMDC growth using especially based on the selenide material system.
Okay.
There are many.
Thank you for the answer.
Mhm.